Hello and welcome to tutorial 18. Our topic today is chirality, stereoisomers, and Fischer projections. Before we get started, just a quick reminder that the notes to accompany this video tutorial are available online through my website. And with that said, let's go ahead and get started with a little bit of review from tutorial 16, where we first started talking about isomers. So we learned in tutorial 16 that isomers are molecules that are different but have the same molecular formula. And we further learned that there are different types of isomers. So let's go ahead and make a brief flow chart to show the relationships that we already are aware of. So we already know that there are structural isomers. Structural isomers are molecules that have the same molecular formula, but a different connectivity of atoms. So it's right here, structural isomers. Sometimes called constitutional isomers, so I'll throw that in there as well. Constitutional isomers. Okay, so for an example of structural isomers, let's look at butane, and I'm just going to do line structures here, so 1, 2, 3, 4 carbons, and its structural isomer 2-methyl-propane, which has 1, 2, 3, 4 carbons as well, but they are connected in a different order. So both of these molecules have 4 carbons and 10 hydrogens. They have the same molecular formula. But the way that those 4 carbons and 10 hydrogens are connected is different. Here we have a CH3 connected to a CH2, connected to another CH2, and finally a CH3. Over here in the 2-methyl-propane, we have a CH3 connected to a CH, and that CH in the middle of that molecule is then connected to 2 other CH3s. Okay, another type of isomer that we learned about is a stereoisomer. Stereoisomers are molecules that have the same molecular formula and the same connectivity of atoms, but they differ three-dimensionally somehow. And so we have discussed one type of stereoisomers called geometric isomers, also commonly called cis-trans isomers. So I'm going to write that as well. And geometric isomers differ three-dimensionally about a carbon-carbon double bond. Now, some cyclic compounds can also exhibit cis-trans isomers, but we didn't discuss that in tutorial 16, and we're not going to discuss that here in tutorial 18 either. Just thought I'd throw that in there in case that's something that your instructor is going to cover, so you know that that does exist. So let's look at an example of a molecule that has both a cis and a trans isomer. Let's use 2-butene as our example, and again I'm going to use line structures. So 1, 2, 3, 4 carbons with a double bond at the 2 position. The 2 larger substituents can be on the opposite sides of that double bond. And remember that the double bond does not rotate freely like a single bond. It is locked in place. So these larger substituents are locked in place on opposite sides of that double bond. This is the trans geometry. So this is trans 2-butene. And its geometric isomer would be the cis isomer, cis-2-butene, where the largest 2 substituents, the 2 methyl groups, the 2 CH3s, are on the same side of that carbon-carbon double bond rather than on opposite sides. So it's right here, cis 2-butene. Okay. So we're going to add to this section here, we're going to talk about a whole new type of stereoisomers called enantiomers. So let's go ahead and erase and go on to slide 2. Rather than starting out by looking at models, I'd like to start out with a simpler example. We're going to start out by just looking at our hands. Notice that my hands are mirror images of one another, and yet they are not identical. If I try to superimpose my hands, they won't quite line up. If I get all the fingers and thumbs to line up, notice that the palms of my hands are facing in opposite directions. If I correct that by flipping one hand so that the palms are facing the same direction, notice that my fingers and thumbs no longer line up. Objects that are non-superimposable with their mirror images are said to be chiral. And there are many different examples of chiral objects in our everyday life. One additional example, in addition to our hands, would be a right shoe. Its mirror image would be a left shoe, and the two would not be superimposable. They would not be identical. Molecules can also be chiral. When a carbon is attached to 4 different substituents, let's just make one W, X, Y, and Z. So it really doesn't matter what they are, as long as they are different. We call that carbon a chiral carbon. And if we look at the mirror image of this molecule, so pretend that this dashed line is a mirror, and we're going to draw the reflection over here. So W going up, X reflecting, so reflecting forward here, Y, and Z. Notice that the two would be non-superimposable mirror images. So I went ahead and made 2 models just to hopefully convince you of this, and I just made different colors here to show 4 different substituents. So let's hold this up here, so W and X, and then Y coming out at you, and Z going away from you. It's mirror image over here. So the blue is reflecting, the red is reflecting, and the green is reflecting. So these are mirror images. Now if we try to superimpose them, notice that if we get the gray and the red to line up, that the green and the blue aren't going to align. If we fix that by getting the green and the blue to line up, then notice that now our red and our gray are not lining up. So these are non-superimposable mirror images of one another. Chiral molecules that are non-superimposable mirror images of one another are called enantiomers. I'm going to write that down. Chiral molecules that are non-superimposable. I'm going to write SNI just to save myself a little time. Non-superimposable mirror images of one another are related as enantiomers. And I'm going to underline that word because that's such an important word that's the focus for most of what we're doing today in this tutorial. And notice that the term enantiomer is referring to a pair of molecules, always referring to a pair because it's referring to a molecule and its mirror image form. So a pair of molecules. And enantiomers are really very fascinating molecules because enantiomers will have all the same physical properties except for one. So they will have the same melting point, the two molecules will have the same boiling point, they will have the same density. The only physical property that will differ for a pair of enantiomers is a physical property called optical activity. So I'm going to go ahead and erase here and give myself some more room. And we're going to talk briefly about optical activity next. So we just said that a pair of enantiomers will have all the same physical properties except optical activity. Optical activity refers to the ability of a molecule to rotate plane polarized light, which is light that is traveling in one plane. So let's indicate our plane polarized light on the board with this wave. Chiral molecules will interact with light, causing it to rotate. So for our chiral molecule, let's pick 2-butanol. So I'm going to draw 2-butanol right here. So a CH3 and a CH2CH3. So 1, 2, 3, 4. There's our 4 carbons of the butane chain. It's a 2-butanol, so I'm going to put an alcohol and a hydrogen on that chiral carbon. So this is a chiral carbon. It has 4 different substituents. Some introductory students will say, well, that's a carbon and that's a carbon, so isn't that the same? They are not the same. This is a CH3, this is a CH2, CH3. So 4 different substituents. The mirror image of this molecule will be non-superimposable with it. So it will be its enantiomer, and the OH and the H would be flipped. All right. So again, we said that a chiral compound will interact with light, causing it to rotate. I'm going to indicate that with this little red curved arrow here. So the light coming out on the other side will have rotated, and we can measure the degree of that rotation with a device called a polarimeter. I'm going to write that up here. Measure the rotation with a polarimeter. Now, 2 enantiomers will always rotate light the same number of degrees, but in opposite directions. The enantiomer that rotates the light to the right is called the dextrorotatory molecule. The enantiomer that rotates the light to the left is called the levorotatory compound. I'm going to write that down. Okay. So the dextrorotatory compound is the compound that rotates light to the right. And we indicate that with the plus sign. The levorotatory compound is the one that rotates light to the left. And we indicate that with the minus sign. So the two enantiomers of 2-butanol can be distinguished by writing them as plus 2-butanol and minus 2-butanol. The dextrorotatory enantiomer will rotate plane polarized light positive 13.5 degrees. So I'm going to indicate its specific rotation here as positive 13.5 degrees. So hopefully you already know what the specific rotation will be for its enantiomer. It's the levorotatory compound, so it's going to be negative 13.5 degrees. Okay, so let's go ahead and erase all of this so that we can go on and talk about the chemical properties of enantiomers. Enantiomers will have all of the same chemical properties, except when they're reacting with other chiral compounds, in which case they can behave very, very differently. So we're going to write that up here on the board. All the same chemical properties, except when reacting with other chiral compounds. So as an example of this, let's just consider the artificial sweetener aspartame, which is a chiral molecule. So if aspartame and its non-superposable mirror image form, its enantiomer, we're reacting with something that is achiral, something like water in a hydrolysis reaction. The two enantiomers would react the same exact way. They would be hydrolyzed at the same bonds. They would form similar products. However, if they're reacting with another chiral molecule, they can behave very, very differently from one another. Let's consider the chiral molecules within our taste buds, the chiral receptors. Aspartame will react with those chiral receptors to produce a sweet sensation. We use it as a sweetener, so that's not surprising. So, reacts with chiral receptors to produce a sweet sensation, sweet flavor. Its enantiomer, its mirror image form, will react with chiral receptors in our taste buds to produce a bitter sensation. So it's right here. Its enantiomer will react differently with chiral receptors, producing a bitter flavor. So very different reaction there, very different result as well. All right, so we're going to go ahead and erase here and go on to talking about one last thing from slide 2. So we are still on slide 2. We're going to talk about finding an internal symmetry plane, which is really the easiest way to be able to determine if a molecule exists as a pair of enantiomers. So far, the examples that we've been using have been pretty simple molecules, but of course you're going to run into more complex problems. So what I'd like to do is introduce the simplest way that I know of to determine whether or not a molecule as a whole is chiral or achiral. So therefore, whether or not it will exist as a pair of enantiomers or not. And the simplest way that I know of to do this is to look for an internal symmetry plane within the molecule. I'm going to write that up here. Look for an internal symmetry plane. I'm just going to write ISP within the molecule. If the molecule has an ISP, an internal symmetry plane, then that molecule is achiral. It will not have an enantiomer. Its mirror image will be identical to it, not a non-superimposable mirror image form. If a molecule lacks an internal symmetry plane, that molecule is chiral. So it does exist as a pair of enantiomers. All right, so I've got 3 examples drawn out on the bottom of slide 2. We're going to go through these 3 examples and look to see if these molecules have an internal symmetry plane and whether or not they are chiral or achiral. So starting out with this first problem here, which is just a CH4, just a methane, and I went ahead and built a model of it as well. So I've got my hydrogen, carbon, hydrogen, and then my other 2 hydrogen, one coming out at you and one going away from you. So you probably can already see, because this is a simple molecule, that there is no chiral carbon here. This carbon is attached to 4 things that are the same. They're all hydrogen, okay? But I really want to focus on the internal symmetry plane. This molecule actually has several. If we draw a line, a plane that passes through this hydrogen, this carbon, and this hydrogen. So a plane cutting through like this. Notice that the hydrogens on each side of that plane would reflect. Maybe I'll hold it this way for a second. They would reflect. Okay. And I have a little piece of paper that I thought might help if I use that as my plane. So again, we're cutting through this hydrogen, this carbon, and this hydrogen. See that the other hydrogens will reflect. So that is what we mean by an internal symmetry plane. And this molecule has several of them, because you could do that with any 2 hydrogen and carbon. Then the others 2 hydrogens would reflect. So these 2 hydrogen and this carbon, the other 2 hydrogen would reflect. Okay, so we're going to say here, I'll write it in blue, that this molecule has several ISPs, internal symmetry planes. Therefore, this is an achiral molecule, and it will not have an enantiomer. Its mirror image will be identical to it, so no enantiomer. So moving on to our next example, which is the bromoethane. So we've got a hydrogen, a bromine, and a CH3. So we can already tell that this is not a chiral carbon because it's not attached to 4 different substituents. So again, a fairly simple example, but the point here is to show you what I mean by internal symmetry plane. So again, I've made a model. I simplified it just a little bit. So you can see my hydrogen, my carbon, and my hydrogen. Let me turn it the correct way there. My hydrogen, my carbon, my hydrogen. And then I made the bromine, this green atom coming out at you. And then I just put another carbon here. I didn't attach the 3 hydrogens because it started to look a little busy with all the hydrogens on it. And that was kind of defeating the purpose of what I was trying to show here. So I just kept it simple with just a carbon there. So we can see with this molecule that we would still have an internal symmetry plane. It would have to cut through, we only have 1 this time, it would have to cut through the 2 carbons and the bromine. And then the 2 hydrogen would reflect on each side. So again, I'm going to grab my little piece of paper here and just show my symmetry plane. A little piece of paper there. That's my symmetry plane. And notice the reflection, the perfect reflection, the symmetry on each side. The 2 hydrogens will reflect. All right, so let's write here that it has an internal symmetry plane, runs through this carbon, and this bromine. Okay, the 2 hydrogen will reflect. Therefore, this molecule is also a chiral, and its mirror image will be identical to it. So it does not exist as a pair of enantiomers. No enantiomer. Okay, last but not least, our last example over here, we have a bromochloroethane. So let's see, I've got my model here. So we have a hydrogen, a bromine, a chlorine, and a CH3. And I just used 3 different colors just to indicate, or 4 different colors, just to indicate that all 4 of these things are different. So this clearly we can see this is a chiral carbon. But again, my point here is to show you what I mean by internal symmetry planes. We're going to look at this molecule and we're going to see if we can find an internal symmetry plane. If we pass a plane through any 3 atoms, notice that the other 2 atoms will never reflect. Doesn't matter which 3 you pick, the other 2 are always going to be different colors. They're always going to be different atoms, different colors in my model. So they're never going to reflect. So no internal symmetry plane, no matter which 3 atoms we choose to try to draw a plane through, the other 2 are never going to reflect. No ISP. This molecule is chiral. And its mirror image will be non-superimposable with it. It will be an enantiomer. Okay, so we're going to go ahead and erase here and go on to slide number 4 and talk about a specific way to start drawing molecules called a Fischer projection. Single bonds can rotate freely, resulting in different conformations of the same molecule. Well, when we're trying to compare 2 molecules and determine the relationship between them, are they identical? Are they enantiomers of one another? Are they diastereomers, which is a type of stereoisomers that we haven't actually talked about yet? It's really important in this case to be drawing the molecules in a consistent way. Fischer projections allow us to draw 3-dimensional molecules easily in 2 dimensions in a very consistent way. So I'm going to take this 3-dimensional model here and I'm going to go ahead and hold it like so. Okay. Notice that it is a chiral carbon here. I have a blue, a green, a red, and a gray. So 4 different atoms indicated attached to that chiral carbon. So a chiral carbon here in the middle. And I'm going to hold it so that these 2 atoms, the blue and the red, are going away from me. Okay, so the vertical atoms are going away from me. So I'm going to draw the dashed line, and let's just say the blue is bromine and the red is fluorine. Doesn't really matter, they're different. All right, and then the horizontal atoms, the gray and the green, are coming out at you, like they're going to hug you. Like 2 little arms coming out to hug you. Okay, so let's make this one a chlorine and a hydrogen. Okay, so in a Fischer projection, we would draw the chiral carbon as the intersection of 2 lines. So this point where the 2 lines intersect, that is our chiral carbon. Let me write that here. Chiral carbons are drawn as the intersection of 2 perpendicular lines. Okay, I'm just going to abbreviate perpendicular there. So here's our chiral carbon. And then everything that is shown on the vertical line is indicating a bond that's going away from you. These bonds, going to the blue and the red, are going into the plane of the whiteboard. Okay, so our bromine would be here, and our fluorine would be here. So I'm going to write down here, vertical bonds are moving into the plane. Okay, so they are going away from you. Horizontal bonds, so these 2 here, the horizontal bonds are coming out of the plane as if they're going to hug you. Okay, so horizontal will hug you. I had a student who came up with that, and I thought it was very clever. All right, so I'm going to write that down here. Horizontal bonds are moving out of the plane. They are coming toward you. All right, so this is a 2-dimensional way to represent, in Fischer projection, this 3-dimensional molecule. And it gets very, very helpful, particularly when you get to larger molecules with 2 or more chiral carbons. All right, so let's go ahead and move on and do a few more examples that are already drawn out for you on slide 4. A few more examples using Fischer projections. When you have 2 or more chiral carbons in a molecule, like we do in this molecule here, life gets a little bit more complicated due to the presence of an additional type of stereoisomers called diastereomers. Diastereomers are stereoisomers that are not related as enantiomers. Now we can figure out the maximum number of possible stereoisomers for a molecule by looking at the formula 2 to the n, where n is equal to the number of chiral carbons. I'm going to write that down. Okay, so there will be as many as 2 to the n stereoisomers. Where n is equal to the number of chiral carbons. So for a molecule that just has 1 chiral carbon, the formula is 2 to the 1 for a total of 2 stereoisomers. And those stereoisomers will be related as enantiomers. So not so hard when there's just one chiral carbon. Okay. So when there's 2 chiral centers, like in our example here, you can have as many as 2 to the 2 for a total of 4 possible stereoisomers. Now clearly the term enantiomer refers to a pair, so all 4 cannot be enantiomers of one another. Some of them are going to be related as diastereomers. So let's go ahead and take a look at this example here. Let's start out with just making sure that we understand the Fischer projection representation. Okay, remember that everything that is in the vertical, has a vertical bond, is going away from you into the plane. All of the horizontal bonds are coming out at you. Remember that horizontal will hug you. Okay, so for this 1, 2, 3, 4, this 4 carbon backbone, that means that that 4 carbon backbone has a C shape, where that C is facing into the plane of the whiteboard. Okay, so a C shape. So let me grab my model here. I've got my 1, 2, 3, 4 carbons in the black atoms. And then I've got a hydrogen in gray, oxygen, hydrogen over here in the red and the gray, and then my second chiral carbon here, hydrogen on one side and OH on the other side. So again, focusing on the vertical, it has a C shape. Let me turn it the other way again, C shape, okay. So they're going into the plane of the whiteboard. I'm going to do that closer to the camera as well. So I'm going to turn it sideways so you can just see that C shape that's pointing into the plane, going away from you. And everything on the horizontal is coming out at you. So that's how you interpret those Fischer projections. It's very, very important that you understand what a Fischer projection looks like three-dimensionally. Okay, so hopefully you recognize already, without me even saying so, that this molecule has an internal symmetry plane. I'm going to draw a line to represent the internal symmetry plane. That means that this molecule as a whole is achiral. It cannot exist as a pair of enantiomers. Its mirror image is going to be identical to it. So just to show you with the model, just to show you that internal symmetry plane, I'm going to go ahead and take my little piece of paper and put it right there. There's my internal symmetry plane. Notice that everything is reflecting perfectly. The top alcohol is reflecting with the bottom. The top hydrogen on the chiral carbon is reflecting with the bottom hydrogen off of the chiral carbon. And the 2 carbons of the backbone are reflecting as well. All right. Okay, so if we try to draw a mirror image here, we'll see that is perfectly superimposable. Let's go ahead and do it just to prove it to ourselves. Not a bad idea to just prove it. Okay, so I'm drawing the OH is reflecting. Okay, so this is its mirror image form. I'm going to put a little dash here so that you know that I'm trying to draw the mirror image of this molecule. Well, all we have to do is take this molecule and flip it and lay it right on top of the other one, and we can see that they line up perfectly. They are superimposable. I'm going to go ahead and also do it with the models here, okay? So not just like this, but just flip it and everything lines up perfectly. They are superimposable. So let me do that one more time, okay? So here they are, and then I'm just going to lay this one right on top of the other one, and everything lines up perfectly. They're identical to one another. They are not related as enantiomers. These two molecules are the same. So I'm going to erase that second one, because it's just the same molecule, redrawn. And I'm going to label this molecule A. Okay. And then we're going to draw another molecule, we'll label it B, where we flip one of these stereocenters, but leave the other one alone. Okay, so let's draw the stereoisomer. Where the first chiral carbon has the same orientation. Okay, so these are the same, but we're going to flip the second one. So clearly, these molecules are still related as stereoisomers. They have the same molecular formula, they have the same connectivity of atoms, CH3, followed by a chiral carbon attached to an OH and an H, followed by a second chiral carbon attached to an OH and an H, followed by another CH3. So same connectivity of atoms. How they differ is in the three-dimensional orientation of those atoms. So let's label this one B. And how are A and B related? Well, they are stereoisomers that are not enantiomers. They are not mirror images of one another, nor are they the same. They are related as diastereomers. I'm going to write down here that A and B are related as diastereomers. Okay. Well, what about the mirror image of this molecule that we're calling B? Let's draw a mirror here. And let's see what the mirror image would look like. So this OH reflecting. And then here, the OH is on the other side, reflecting. Okay. All right, so this molecule also lacks an internal symmetry plane. Okay, so it should be a chiral molecule with an enantiomer. So these two here are in fact related as non-superimposable mirror images. These two are related as enantiomers. Let me just prove to you by quickly rearranging my model here. I didn't have enough atoms to build all three of these models. So I have to kind of share here. Okay. Flip that one. All right. So here's this molecule. And then over here, I have the other. I'm going to hold these a little bit closer here. All right. So let's try to superimpose these and just prove to ourselves that these are not identical, but they are non-superimposable mirror image forms, which are enantiomers. Well, if I try to do it this way, obviously my OHs are on the wrong side. Okay, they don't line up. Well, what if I flip it this way? And then try again. Same problem. My OHs are on the wrong side. What if I flip it like this? Oh, then I have my OHs on the correct side. But notice that I just took one of those out of Fischer projection, and now that C-shaped backbone is pointing toward you in one of the molecules and away from you in the other. So my carbon, my 4 carbon backbones do not line up if I get the OHs to line up. So there is no orientation that I can give this model to get it to superimpose on the other, because these are not the same. They are non-superimposable mirror image forms. So I'm going to call this one C. It's its own unique molecule. And I'm going to write the relationship between B and C. B and C are related as enantiomers. Okay. Finally, what about A and C? How are they related? A and C are clearly stereoisomers. You can check the molecular formula, check the connectivity, it's all the same, the connectivity, it's all the same. What is different, again, is just the three-dimensional orientation about some of those chiral carbons. Okay, so these again are stereoisomers that are not enantiomers and are therefore related as diastereomers. So I'm going to write down here A and C are related as diastereomers. Okay, so remember we said with two chiral centers we could have as many as 4 possible stereoisomers. For this case, we only have 3. And the reason we only have 3 is because the first molecule was actually achiral, okay, and therefore it didn't have an enantiomeric pair. So we didn't end up with 2 pairs of enantiomers that are related as diastereomers. We ended up just with 1 pair of enantiomers, which is related to the other compound, the achiral compound, as diastereomers. Just really quick before we go on and look at another example. Molecule A, a molecule that has chiral carbons, but is achiral overall and therefore does not exist as a pair of enantiomers, has a special name. We call those molecules meso compounds. So A, I'm just going to write here by A, this is a meso compound. Again, a molecule that contains chiral carbons, but because it has an internal symmetry plane, it is achiral overall, and therefore it will not exist as a pair of enantiomers. Its mirror image will be identical to it. Okay, let's erase here and look at another example. So for our last problem, we're looking at another molecule in Fischer projection with 2 chiral carbons. We're going to find all the different stereoisomers that exist for this molecule. So we've got as many as 2 to the 2 to the n equals 2 stereoisomers. So as many as 4 possible stereoisomers. All right, so first thing, let's look for an internal symmetry plane. So take a moment to look at that molecule, and hopefully you will agree with me that there is no internal symmetry plane within this molecule. If we tried to draw one here, notice that these 2 functional groups are different. This aldehyde and this alcohol will not reflect, okay? So no matter how you look at that molecule, you will never find an internal symmetry plane. That means that the mirror image of this molecule should be its enantiomer. So let's go ahead and draw our imaginary mirror here and draw the mirror image form over here. Okay, so in the notes, I have this molecule drawn, and I put the aldehyde in a condensed form. I wrote CHO. Remember that that is the condensed form of an aldehyde, but I'll go ahead and draw it out. It's just that when you're typing it out, it's a lot easier to type CHO, but I'll go ahead and draw it out in this example here. And then we've got our OH reflecting and our H reflecting, and this OH reflecting, and this H reflecting, and this CH2OH. Okay, so these 2 molecules are related as non-superimposable mirror image forms. You can think about all the different ways to try to overlap them. If you lay them on top of each other, notice that the OHs are going to be going the wrong way. If you try to turn it like that, notice that your aldehyde would then be going the wrong way and wouldn't line up, no matter how you flip it. If you try to flip it this way, remember that your carbon backbone is now going to be facing the wrong way. So no matter how you try to overlay those two, you'll see that they will never superimpose because they're not identical. They are non-superimposable mirror image forms. So let's label them molecule A and molecule B, and let's write down here that A and B are related as enantiomers. Non-superimposable mirror image forms. All right, so as many as 4 possible stereoisomers. So let's take a look at another stereoisomer for this molecule. Let's flip one, but not the other stereogenic center. All right, so I'm going to draw that over here and label it C. I've still got my aldehyde here. And let's flip the first one, flipping it in comparison to A, not in comparison to B. Okay. But let's leave the second chiral carbon the way it is. Okay, so we're not going to flip it again with respect to A. And then we'll label this one C. Okay, so how does C relate to A or even B? Well, clearly they are stereoisomers. Same molecular formula, same connectivity of atoms, but they differ three-dimensionally somehow. Molecule C is not a mirror image form of either A or B. Okay, if it were, then it would be identical to the other enantiomer over there. Okay, so it is a different molecule. So a stereoisomer that is not an enantiomer, C must be related to both A and B as a diastereomer. So I'm going to write down here, C is related to both A and B as a diastereomer. Okay. Well, C can also have an enantiomer. We just haven't drawn it yet. So let's go ahead and indicate our mirror here. Okay. And draw the reflection. So we've got our aldehyde, H and OH, OH and H, and the CH2OH. And let's label this one D. So once again, no matter how you try to superimpose these, you'll never get all of the atoms to line up because these are not identical. They are non-superimposable mirror image forms. So C is related to D as another pair of enantiomers. So let's write down here, C and D are related as enantiomers. Okay, then how does D relate back to A and B? Well, D is a stereoisomer of both A and B, but it is not an enantiomer of A or B, so molecule D must also be a diastereomer of A and B. Boy, that was a lot to say. Okay, so let's write that down here. So D is related to both A and B as a diastereomer. Okay, so a great example of a molecule that has all 4 possible stereoisomers, which is really 2 pairs of enantiomers that are related to one another as diastereomers. Okay, so again, 2 pairs of enantiomers, and then those 2 pairs would relate to one another as diastereomers. Okay, so we're going to go on to slide 5 and wrap up tutorial 18. So you may be wondering why it is so important to be able to determine if a molecule exists as a pair of enantiomers. It seems like such a subtle difference, 2 mirror image forms. Well, think back to when we talked about the chemical properties of enantiomers. We said that 2 enantiomers will have all the same chemical properties except when reacting with other chiral compounds. In that case, they can behave very differently. Well, living organisms are composed of chiral compounds. So when you start thinking about the medications that you use, many of those active ingredients are chiral. Pesticides that we put on our food, food additives, many of those compounds are also chiral. One enantiomer may be beneficial, the other enantiomer may be ineffective, but it may even be harmful to you. Probably the most infamous example of this occurred back in the 1960s when a drug called thalidomide was prescribed to treat nausea. It was prescribed often to pregnant women who were experiencing morning sickness. One enantiomer, drawn over here, our thalidomide, was responsible for the therapeutic effect. It treated the nausea. The other enantiomer, its mirror image form, S-thalidomide, they found out later was teratogenic. Not only did it not help with the nausea, but it was harmful to the developing fetuses. So we're going to go ahead and end our tutorial 18 right here. And I will just point out that there is one more slide, slide number 6. And slide number 6 is just a summary of all the different types of isomers that we have covered to date, along with their definitions. So one nice slide with all of that information in one place. All right, thank you very much for tuning into tutorial number 18. I hope that you will consider tuning into problem set 18.